Okay, welcome back. So this is the second video in the series for the quantum physics module of Physics 100, where again, I'll remind you we're going to be talking about this paper about measuring the time that an atom spends inside a classical barrier while it's undergoing the process, the quantum mechanical process called tunneling. So the first goal is we want to explain what tunneling is and why this is a characteristic quantum phenomenon. And that has to start with considering the nature of particles and the nature of waves. Right, so this is a photo of the little decorative pond we have in our backyard, and you see sort of examples of both of these things. Right, there's rocks that act like particles, and there's water that has waves in it from the little fountain that we have there. So one route into understanding quantum physics is the notion that particles behave like waves and vice versa. That is, things that we normally think of as having particle character also have some wave character to them, and things that we think of as having wave character also have some particle nature. And combining those two things gets you to quantum physics. Now, in order to explain that, I need to be fairly specific about what I mean by particles and particle behavior and wave behavior. So this lecture is going to be, or this video is going to be a little bit detailed about the basics of that, just as hopefully a lot of this will be reviewed to people who have taken a little bit of physics before or read a bit about science. But if not, this will go into a little bit more detail than I probably will in the live class. So what do we mean when we talk about particles and waves? Well, if we look at this picture of my pond, you can see that there are these rocks that behave like particles. And what do we mean by that? Well, one of the chief characteristics of particles is that they're discrete, right? And they're countable, right? I have some number of rocks in that photo, and I can count them. Right? And I have, one rock, two rocks, three rocks. I never have like a rock and a half. That's not really a meaningful concept. These are discrete entities, right? I can't break them into fractions. I can break a rock in half, but then what do I have? I have two smaller rocks, right? So the characteristic of particles is that they are always discrete, countable objects. Second characteristic, a little more mathematical in talking about these in physics terms, that a particle always has a well-defined trajectory. That is, it has a position at some point that we can measure as a function of time. So we call the position, say, r, and that has an x-coordinate, a y-coordinate, and a z-coordinate. Right? I can write down functions x, y, and z. They're functions of time that tell me exactly where in space that particle is. And this will also have a well-defined velocity at each of those instants in time. So it'll have an x component of velocity, y component of velocity, z component of velocity. Right? I can write down a function v of x, v, y, v, t, vz that are functions of time. Right? So I have a well-defined position as a function of time and a well-defined velocity as a function of time. I know where a particle is and how fast it's moving. Right? And that, along with the discreteness of particles, is sort of the quintessential particle behavior. Right? So the particle is in a particular place at a particular time, moving at a particular speed, and I can define all of those things mathematically. Waves, on the other hand, are a little more slippery. Right? Waves is, you can't say that there's a wave in just one position. A wave is an extended disturbance in some medium. Right? There's a whole pattern of waves that make up the waves in this pond, and they're spread out. Right? Even if I want to just try and like narrow it down to a single wave, right? That single wave extends over some distance. Right? So the waves are continuous and they're delocalized. Right? And it's also they're not really countable. I mean, you can you can count the peaks of the wave that go by, but can you distinguish between one wave and 17 waves? Not so much. Right? There can be many waves happening, and you end up with just one pattern, right? That is a continuous delocalized thing. In mathematical terms, the wave ends up being described by a wave function that is a function that fills all of space, and is a function of the x-coordinate, the y-coordinate, z-coordinate, and of time. Right? So it's a pattern that covers all of space that changes in time. And this is something very different than what you have with particles, right? Particles are localized to a specific place at a specific time, right? But waves is sort of, it's a whole fuzzy pattern that it fills a region of space and changes over time. And that's a very different kind of thing. Now, the lesson of quantum physics that we're going to talk about is that these two sets of properties have to be combined. That things that we think of as particles also have some wave character, and things that we think of as waves also have some particle character. And so these things need to be mixed and mingled together in ways that change our conception of reality. Right? And so this is the thing that we're fundamentally talking about here. So we want to talk about how these things work, right? We can talk about the rules that govern the behavior of particles and the rules that govern the behavior of waves. And hopefully the rules governing the behavior of particles are somewhat familiar. Right? These are things that you would learn well if you took physics in high school, or you get some idea of them even if you just took middle school science, right? So you start with Newton's laws of motion, right? In particular, Newton's second law is kind of the most important. It's the one that says that F equals ma. If you add up all the forces that act on some particle, right, the sum of those forces is equal to the mass of that particle times the acceleration that it will have. So it tells you how the motion of that particle changes in time. Right? Second really important concept in thinking about classical physics of particles is that particles have momentum, right? The momentum classically is the mass of the particle times its velocity. And the really nice thing about this is if you add up the momentum of all of the particles involved in some system, some complicated thing that you're trying to study, you add up the momentum of all of the individual particles, the total momentum you have at the beginning of the problem has to be exactly the same as the total momentum you have at the end of the problem. So whatever interactions they undergo in between, at the end of it, you may have redistributed momentum. You have taken some momentum away from this particle and given it to this one over here. But whatever happens, the total momentum at the end of the process will be exactly the same as it was at the beginning of the process. The third and final piece that we'll talk about here, there's other things you can talk about the behavior of particles. That's a whole other couple of courses. But the other one that's going to matter for us here is particles have energy, right? In particular, we can talk about the kinetic energy of a moving particle. That is 1/2 times its mass times the speed of the particle squared. And we can also talk about potential energy of various kinds, right? So if you have some object that's at a high altitude, right, that has potential energy because it's interacting with the gravitational pull of the Earth, and that means it has the potential to start moving and acquire a bunch of kinetic energy as it falls and accelerates before it hits the ground. Energy is another thing like momentum that has a conservation law associated with it. So I have some system of particles and things that are interacting with each other. I can calculate what's the kinetic energy of each of the particles, what are the potential energies that come from the interactions between these things. And if I add up that kinetic energy plus potential energy at the beginning of the problem, that total is going to stay the same through the whole thing. Right? So at the end of whatever complicated thing goes on, right, the total kinetic energy plus potential energy stays the same. Right? So if I start off with a ball in a high place and drop it, that starts out with potential energy. As it falls, it turns that energy into kinetic energy. But the sum of those two things, the kinetic energy plus the potential energy, is always the same. And that's an extremely useful principle in understanding the behavior of particles as they move in Newtonian physics. Now, the other category of objects we need to think about are waves. All right? And waves are a little more complicated because of this continuous and delocalized thing. But there's some basic building blocks that go into wave physics. And what we think about is what's called a single frequency traveling wave as our starting point. So it's a pattern in space that looks like a sine wave, right? It's a sinusoidal oscillation in space, and it's moving. So as time goes by, it shifts from one place to another, right? So that whole pattern just sort of moves over from left to right as you go along. All right. We characterize waves by a few parameters that go into them. Number one is the amplitude, which is just the height of the wave, right? So I have a wave that, I have some medium that's displaced up by some amount, down by some amount, right? Up to the peak of the wave, down to the crest of to the valley of the wave. And the distance between the rest position and the peak, or the rest position and the valley, or half the distance between the peak and the valley, that's called the amplitude. That's the height of the wave. All right. The wave also has a wavelength. All right. A wavelength is what you would see if you take a snapshot of the wave and then measure the distance from peak to peak, or the distance from valley to valley, or even the distance from zero crossing to zero crossing, you know, the distance that it needs to go through one full oscillation, the distance over which the pattern repeats. The final property that we talk about when we're discussing waves is the frequency, or the period. The period is the time that you need for one oscillation to occur. So if you sit in one spot and watch the wave go by, right, you will see it takes some amount of time for you to be at the peak of one wave, to go down into the valley and back up to the peak of the next wave. As that wave passes you, the time that's needed for that to happen is called the period. And then the frequency is 1 over the period. It's the period is the time needed to do one oscillation. The frequency is how many oscillations does this wave do in 1 second. Those three things are the crucial parameters for talking about waves, right? We have the amplitude, the wavelength, and the frequency are the things that go together. There's also a key relationship between the period and wavelength and frequency and the speed of the wave. And that is that the period is the time that it takes the whole wave pattern to shift over by one wavelength. Right? And if you know that, then that tells you that, well, the speed of that wave is one wavelength per period, or the speed is equal to the wavelength times the frequency. This is a really useful relationship because frequently we know, say, the wavelength of light, but we need to calculate something that involves the frequency of that light. Those two things are closely related because we know that the speed of light is going to be equal to the wavelength multiplied by the frequency. And so, you know, we use this a lot when we're talking about light because sometimes we know the wavelength, but it's more convenient to deal with frequency, and so we can convert from one to the other very easily. So this relationship that the speed of light c is equal to lambda times f is a very important one for working with waves as a practical matter. With all of these things together, you know, I said that a wave needs to be described by a wave function. What does that look like? So here's an example of the mathematical function describing a wave. So it's a function of both position and time. I'm going to start with just a one-dimensional wave that's moving from left to right. And the way we typically write this is as a wave function. It's a function of position and time. That'll be the amplitude multiplied by the sine of, then in parentheses, we write it as kx minus omega t. We do this for two reasons. One is that the k and omega are expressed in radians per whatever, because that's what we need to have, right? We're going to work with these trigonometric functions. We want an angle in radians for that to work with, so we need radians per something in there. So we express the frequency as an angular frequency. It's 2 pi times the regular frequency f, just to convert it to radians. And then the wavelength shows up as this wave number k, which is 2 pi divided by the wavelength. So it's 2 pi to convert it to wavelengths, to radians, and then divided by the wavelength because what we really want is x over lambda. And then this is where the second reason for redefining these things comes in, which is we're kind of lazy as physicists, and like having to typeset things that are on multiple lines, like fractions of both the numerator and the denominator, is kind of annoying. So we redefine k as a thing that has a 1 over lambda in it, and then I can write the whole formula on one line. So what are the pieces of this, right? This you know, wave function phi, the lowercase Greek letter phi that I'm using here. This is the function that tells us describes the wave pattern. A is the amplitude of the wave, and x is the distance from wherever the wave starts, the source of the wave, to whatever position I'm interested in measuring it. Okay, and this formula, this a sine kx minus omega t, this is a wave pattern that changes in time in a way that corresponds to a wave moving from left to right. It has a frequency f, right? It has a wavelength lambda. Those are hidden in this k and omega. And this describes that kind of traveling wave. It's a single sinusoidal wave in one dimension moving from left to right. And once we have this, this is sort of the building block for everything else. I can expand this to multiple dimensions in a relatively straightforward way. I can talk about multiple waves by just adding different waves together. So this is the key building block for talking about the physics of waves. So now we have these two things, right? We have these laws that govern the behavior of particles, Newton's laws, conservation of momentum, conservation of energy. Those things go together to describe the behavior of things that are particles that have a definite position at a definite time. And then we have these wave functions, these traveling waves, that describe the behavior of waves as that are, you know, delocalized. It's a whole pattern that's moving in space. All right. And what our goal is in doing quantum physics is we need to combine these two sets of properties, right? We need to take these two things and put them together and have everything in the universe behave a little bit like a particle and a little bit like a wave at the same time. Why that is and how we know that's true is something, though, that is going to be the subject of the next video lecture, so, you know, stay tuned for that.